if you saw Monday's video, on Monday, we talked about momentum equation, right? So we started this new topic where we studied Newton's second law of motion from the context of a control volume. So just as a review, on Monday we talked about the conservation of momentum, and specifically we derived an equation called the momentum equation, right? Now if you don't remember, that's all right, we're going to review it. The momentum equation said that the sum of forces in a system was equal to the mass flux in the system times the velocity leaving the system minus the velocity entering the system. Now we arrived at this equation through a couple of assumptions, right? We assumed that our flow was going to be steady and uniform, which is what you will see when you're working in industry. But notice that because we have two flux terms, we actually assume that flow comes in and flow goes out through, I guess, some control area or some control surface. Now the reason I want to point this out is because this V out minus V in is essentially equal to the net flux of velocity, which was our intensive property, through the control volume. Now we call it V out and V in because we say, well, some of it has to come in, some of it has to go out, right? However, you may have situations where you can have two outlets and one inlet, or vice versa. You can have situations where you have two inlets and one outlet. So when that happens, remember, you'll have multiple V out or V in terms. So for example, in this scenario where you have flow coming in through one inlet and leaving through two outlets, you're going to have two V out terms and one V in term. The two V out terms are still going to be positive, and that one V in term is still going to be negative. Likewise, if the situation was reversed and you had flow entering through two inlets and leaving through one outlet, you would have one V out term and two V in terms. And that one V out term will still be positive, but those two V in terms will be negative. So when you see V out minus V in, don't think that it always has to be two terms. Sometimes you may have more. So today I would like to work on an exercise where we have more than one inlet or outlet so that we can get used to this scenario. Now that's one thing. The second thing is, from continuity equation, and this was talked on Monday, we got that mass flux in equals mass flux out for steady uniform flow in a non-deforming control volume. But again, we may have multiple mass flux ins, we may have multiple mass flux out. So what matters from a continuity standpoint is that your mass flux ins, right, equal your mass flux out, however many they may be. In other words, if you have two outlets, then the sum of those two outlets should equal that one inlet, and vice versa. Now we're gonna look at all this in an actual example, but I do want to prepare you that sometimes the equation may not be as straightforward as what we have just derived, and it's okay when you see an equation that's not as straightforward, right? So just to avoid confusion, I would recommend that everybody rewrite this equation in the following way. I would recommend that instead of setting out your mass flux as just one individual term, perhaps you may want to include your mass flux for each individual inlet and outlet. Of course, if you have only one outlet, one inlet, then this can be factored out. But if you have multiple outlets and multiple inlets, it's a little bit different the way you factor them out. So what I'm going to do is I'm going to write the equation in this way so that when we work on an example, you can see how I can factor out my mass flux. So this was the momentum equation. During the last 5 minutes of Monday's class, we applied this momentum to the case of deflectors. Now we define deflectors as any solid structure that deflects, that means that changes the direction of flow. And we said that we can find deflectors pretty much anywhere. So at the smallest level, we talked about a spoon, right? You open your faucet, it hits your spoon, it splashes water everywhere, right? Because the spoon is a deflector that changes the direction of your flow. At the larger level, you have your car, your windshield, right? Your car is moving, air is a fluid, so the windshield changes or deflects the direction of air particles as they travel through your car. Now, deflector theory, we said, was pretty much based on the momentum equation. with some simplifications. When we're dealing with deflector theory, we know that we have an angle of deflection, because if there's no angle of deflection, there's no deflection, there's no momentum change. And we said that we can deal with deflectors by defining their angle of deflection, and we could use that knowledge to come up with some fluids equations that apply specifically to deflectors. Now, what are the limitations? Typically, for deflectors to apply, the flow has to be open to the atmosphere, right? So if the flow is open to the atmosphere, the pressure everywhere in the flow is atmospheric pressure. So why does that matter? Because if the pressure is atmospheric pressure, then we don't really have to consider any pressure forces in this sum of forces terms. So we said that if we want to find the sum of forces in the x direction of this system where you have your deflector, and the deflector is held by a horizontal and a vertical reaction force, then we said that the sum of forces in the x direction should be equal to negative my reaction force, negative because it's just pointing to the opposite direction of flow, and that from the momentum equation is equal to mass flux out, V out minus mass flux in, V in. But of course, we're only looking at the x component of those velocity components. And why does that matter? Because if your flow enters your deflector with one velocity, leaves your deflector with the same velocity, then we can find these components as a function of the magnitude of the velocity and the angle of deflection. So we said that in the x direction, you had that the outlet velocity, the velocity of the fluid leaving the system, was equal to velocity times cosine of alpha. Is that correct? Okay. I think you should be able to see it, right? You have a triangle, velocity alpha, what's this horizontal component? Velocity times cosine of alpha. And then we said that the inlet component of the velocity is just velocity. We could factor out this velocity to say that the reaction force in the x direction, negative, is equal to mass flux times velocity times cosine of alpha minus 1. And then we can simply multiply both sides by -1 to obtain that the reaction force in the x direction for the deflector is equal to mass flux times velocity times 1 minus cosine of alpha. And what does this tell us? Well, the greater your angle, alpha, then the greater the reaction force needed. In other words, the greater the force from the fluid. So the greater the deflection angle, then the bigger the fluid force. We did the same thing in the y direction, where we said that the sum of forces in the y direction were equal to just the reaction force in the y direction. And that was equal to mass flux times velocity, mass flux times velocity out in the y direction minus velocity in the y direction. And here we see that the y component of this velocity is just velocity times sine of alpha. Is that correct? So we get that Ry is equal to mass flux times velocity sine of alpha. And then we get that the y component of the velocity entering my deflector is what? 0, right? So I get an equation of Ry equals mass flux times velocity times sine of alpha. So these were my two deflector equations. And again, they're very simplified, as you can see, because with these deflector equations, we assume several things, right? We assume that there's only one inlet, one outlet, and all that stuff. So what we're going to do now is we're going to see how we can apply these deflector equations into systems that have more than one inlet. Now, instead of deriving theory for that and coming up with an equation, we should just work strictly on a problem, because different systems are going to yield different equations, right? So we can't really derive an equation for each and every system that you're going to see. I think the best thing we can do is we can start with the general equation and then learn how to simplify that equation based on your system. So what we're going to do now is we're going to look at a simple example from the book where we have flow from a hose being deflected in two different directions. By the way, are there any questions up to this point? Yes?
Why is the Rx negative again and the Ry is positive?
So when fluid travels through the deflector, it's exerting a force on the deflector. So in order for the deflector to remain static, moving, it needs to apply these two forces. Okay? So remember, if fluid travels to one side, the force will push towards the other side. So the deflector has to resist that force. Okay? Any other questions? So if there aren't any other questions, let's go ahead and start with an example. I'm going to keep these deflector equations there. But remember, we may not go to those simplified equations. We're going to start with the general momentum equation and then deal with that equation, okay? So we have flow coming from a hose. Don't take my drawing as the best. Instead, I recommend that you look at your example on the book, okay? So we have flow coming in from a hose that has a nozzle diameter of 1 inch. The flow is water, yeah, it's water. So all we have is water here traveling from a hose, and the flow hits a small ridge that deflects the fluid. In other words, part of the fluid travels in one direction, part of the fluid travels in another direction. So this is a solid boundary. Flow travels from this hose and deflects in two directions. We're given a couple of information, right? This is water under standard engineering conditions. We are told that the hose itself is at 45 degrees from the horizontal, and we're told that this is at 60 degrees from the horizontal, and this is simply a vertical wall. We're also told, okay, that water is discharged from this nozzle at 180 gallons per minute. So the flow rate leaving this nozzle is 180 gallons per minute. So that's how much water leaves the nozzle per time. Okay. Once the flow strikes the surface, 3/4 of the flow are going to move along this direction. So we can call this our inlet, we can call this our outlet, and this our outlet. So 3/4 of the flow are going to move in this direction. And then 1/4 of the flow is going to travel in the upwards direction. Now the question is, what are the x and y components of the resultant force that is exerted on this surface? So first, before we even start to solve it, let's see if we can actually understand what we are looking at. Okay? So we look at this diagram. Okay? We can select our control volume, and just by looking at the diagram, I would recommend that we select our control volume before the deflection, because if our volume is before the deflection, then we can account for any exchange of momentum that occurs when the water changes direction. So we can select our control volume to be just before the deflection and end just after the deflection. Now, if this is our control volume, Rami, how many inlets do I have and how many outlets do I have?
1 inlet and 2 outlets.
That's correct. Does everybody agree with Rami? 1 inlet and 2 outlets. Good. So if I were to write my momentum equation, what would it look like? Let's see. I have about my sum of forces equals mass flux out, velocity out. But this is actually divided into 2 outlets. So I'm going to give them numbers, okay? I'm just going to say that this is the inlet. And this can be my first outlet, the one that has the most flow. And this can be my second outlet, the one that has less flow. So we have mass flux out, velocity out 1, plus mass flux out, velocity out 2, minus mass flux in, velocity in. Now, why am I not factoring out the mass flux? Because notice that whatever comes in will go out, we know that. However, because it's being distributed, this mass flux in is not equal to this mass flux out, right? And it's not equal to this mass flux out. Rather, it is the sum of these two that will equal this mass flux in. So we can't factor it out just yet. We can't just say, okay, factor out mass flux and you got your velocities. We need to consider, right, what is the distribution of flow in the system. Now, because we want to deal with equations that, or units that we're already familiar with, let's go ahead and convert these into standard US customary units. We're told that our flow rate is 180 gallons per minute. and there are 7.48 gallons in every cubic foot. So we're going to just go ahead and do that conversion quickly. We have the flow rate is 180 gallons per minute. How many seconds in a minute? Okay. So we can divide this by 1 minute, or 60 seconds over 1 minute. Yeah, we divide it by 60 seconds over 1 minute. And then we can also multiply it by 1 cubic foot over 7.48 gallons. You don't necessarily have to have these units conversions memorized, at least not for this class, because our tests are all open book, open notes. But sometimes it's helpful to at least know how to convert the units, right? Good. So we notice that gallons cancels out, minutes cancels out, and we end up with how many cubic feet per second of flow, at least at the inlet. 0.4. Is that it? Can you give it to in 3 significant units?
0.401.
Thank you. Good. Now, to what mass flux does this flow rate correspond?
To the inlet.
The inlet, right? So only to this one. Okay. So let's make sure that we understand that this mass flux only corresponds. This flow rate only corresponds to this inlet mass flux. Okay. Now, when it comes to velocities, however, we can be a little bit more generous, because notice that our deflector theory, right, shows us that the velocity magnitude remains constant. So even though flow rate may change, the magnitude of the velocity should remain constant through a deflector. Of course, if flow rate changes but velocity doesn't, then of course area needs to change. But we're not going to look at area for now. For now, let's focus on these velocity terms. Okay? So I'm going to call this Q in because we know this is the flow rate entering the system. How about we find out what this velocity entering the system is? How can we find that velocity entering the system?
By Q divided by area.
That's true. Q in over the area of the inlet. We know that Q in is 0.401 cubic feet per second. And what about the area? Well, we have a 1-inch nozzle, so the area will be 1 over 4, pi over 4, times 1 over 12 squared, feet squared. So we get a velocity entering my system of how much? Yeah, go ahead.
To find the mass flux, can you just times the 0.40134 to find that flow? This is the first outlet.
Yeah. That's what we're going to do, yeah.
You can add them up.
Yep. We're going to do that, don't worry. So what's this velocity?
73.53.
Thank you, 73.5 feet per second, right? Now, of course, I try to keep everything to 3 sig figs, just for clarity. But if you are using a calculator, then just keep the number complete, right? Keep as much as you can until you get to the end to avoid rounding errors, okay? Thankfully, this is not a class where rounding errors are going to destroy your calculations. But in the future, who knows? When you're dealing with, you know, these tiny microfluidic devices, or when you're dealing with very, very, very large systems, then maybe rounding errors may be significant, okay? Not for this class, but just as a general recommendation. Good. So we have our velocity in. And why does that matter to us? Because since velocity does not change across the deflector, then this velocity should be equal to this velocity, which should be equal to this velocity. Note that I'm saying velocity, not flow rate. This is just linear movement, not quantity. Okay? So that means that my velocity in is equal to my velocity out at the first inlet, and also equal to my velocity out at the second inlet. So let's go ahead and calculate, right, the sum of forces in the system, in this control volume. We know that we typically don't like to deal with vector notation here, so we're going to split this vector up into its rectangular components of the x and y directions, right? I think we're all familiar with how to do that, right? So we get that the sum of the x component of the forces equals my mass flux out times the x component of my velocity leaving the system for the first outlet plus my mass flux out times the x component of the velocity leaving the system for the second outlet minus my mass flux in times the x component of the velocity entering the system. So now we're dealing with scalars. We're not dealing with vectors. That's good. We can just add these numbers up as necessary in our calculators. Okay. So we have this system. We have Q in. So with Q in, we should be able to get mass flux in. And we don't really have a specific value for Q out, but we know the distribution of flow. And if we know the distribution of flow, we should be able to calculate the flow rates. And we should be able to calculate the mass flux. Now, how can we simplify a system? I'm going to go back to something Rami said earlier. If we know the flow distribution, then we should be able to calculate your flow rates, right? And there's two reasons for that, right? Number one, we know that mass flux in equals mass flux out. In this case, mass flux in will equal my two outlet mass fluxes, right? What that means is that the sum of these two mass fluxes should be equal to whatever's coming in. Now, of course, water is an incompressible fluid. And if it's an incompressible fluid, we know that density doesn't change with respect to pressure. And because we don't have any pressure differentials here, we can essentially treat our density as a constant, right? So we can say that density times flow rate in is equal to density times flow rate out 1 plus density times flow rate out 2. And how does that help me? Well, I see that flow rate in should be equal to flow rate out 1 plus flow rate out 2. And of course, we already have those distributions. But notice that even if we didn't have both distributions, we could still figure out, all three of these flow rates as long as we have flow rate in and at least one of those distributions, right? So we know that flow rate in is equal to flow rate out 1. And we said that through the first outlet, only 3/4 of the flow rate travel, which means that this flow rate out 1 is simply equal to 3/4 of flow rate in, right? And then flow rate out 2 is equal to 1/4 of flow rate in. Add these up, you get 4/4 flow rate in, and just flow rate in equals flow rate in. So what I want to get at with this is that as long as you know the flow rate and the distribution, you should be able to calculate all your other flow rates. Now, of course, this is flow rate, not mass flux, but you know that if you multiply these terms by density, then you get your mass fluxes. Okay, so it is not that big of a difference. Now, let's go ahead and just deal with mass flux, since we're already dealing with mass flux. If I know that flow rate in is 0.401 cubic feet per second, what is that mass flux equal to, mass flux in? Sorry?
Shouldn't just be that number right there?
Well, flow rate is 0.401, right?
Yeah.
So what is mass flux in?
Oh, okay, I see what you're saying. 981.
Okay. So what's the density of water for English units?
62.4.
The density of water. 1.9 for what? Slugs per cubic feet. If you forgot it, it's okay. Let's say you forgot. Who said 62.4? All right, Andy, let's say that you forgot the density. You don't have your notes, right? And you lost your tables. You forgot the density, but you know that the specific weight is 62.4, right? How can you go from that to the density?
Divide by the gravity.
Exactly, right? So if you forget the density, but you know the specific weight, just divide it by the gravity, and you'll get 1.94. So divide 62.4 by 32.2, and you'll get 1.94. So it's good that you mentioned it, right? Because it's always good to be able to relate all these properties. So 1.94 slugs per cubic feet times our flow rate of 0.401 cubic feet per second. That gives us a mass flux entering my system of how much?
0.778.
Slugs per second, right? Because cubic feet cancels out. Good. What about my mass flux leaving through the first outlet? We said that that's 3/4 of the total mass flux, right? So that's just 3/4 of mass flux in, or simply 3/4 of 0.778. Now, I personally like to organize my equation before I start plugging in numbers. If you like to solve the numbers first and then plug them in and then solve your equation, that's also fine. But what I'm going to do, and you don't have to do this, just my personal preference, I'm going to leave my mass flux out as an expression of mass flux in. And I'm going to leave my other mass flux out also as an expression of mass flux in. I think you can see why I'm doing that, right? Because now I look at my equation and I say sum of forces in the x direction equals mass flux out times V out for the first term in the x direction. Mass flux out, V out for the second outlet in the x direction. Mass flux in, V in the x direction. But because my mass fluxes leaving the system are actually functions of my mass flux entering the system, then I can factor out that term. Does that make sense? If it doesn't, let's just go ahead and write it on the board. So we get that sum of forces in the x direction equals what? Well, in the x direction equals mass flux out for my first outlet. But we know that for the first outlet, the mass flux is only 3/4 of whatever was coming in, right? So I can write this instead as 3/4 of my mass flux in, right? Times the x component of V out.
Shouldn't that just be 0?
Sorry?
Shouldn't that just be 0?
It will be 0, yeah, for now. Well, let's write the whole equation first. And then my mass flux out through my second outlet will be equal to what? Well, we know that only 1/4 of the entire flow rate travels in the second outlet, so it'll be 1/4 of my mass flux in times V out x for the second outlet. And finally, I get minus mass flux in V in the x direction. So this is why I prefer to express my mass fluxes in terms of whatever the initial value was. Just because it helps me simplify my equation just a little bit. You don't have to do it this way, right? You can do it a different way if you prefer, but that's just how I will choose to do it, okay? So what do we have? Well, notice that I have that my sum of force in the x direction is equal to, I can factor out my mass flux in. Does that make sense? I'm factoring out my mass flux in. So I get mass flux in multiplied by 3/4 of the x component of the velocity leaving the system plus 1/4 of the x component of the velocity leaving the system through the other outlet minus just 1, the velocity entering the system. Does that make sense? Good. Notice that we can, so far we haven't really dealt with anything specifically x related, so we can actually use this equation for my sum of forces in the y direction as well. Just change your x subscripts for y subscripts. But now that we have our slightly more simplified equation, we can go ahead and solve it. We get that the velocities are the same, still 73.5. So let's just go ahead and solve this equation. We get that sum of forces in the x direction equals what? Mass flux in, yes, we know, but mass flux in was 0.778 slugs per second multiplied by 3/4 of the x component of my velocity leaving through the first outlet. Let's call this my x-axis. Let's call this my y-axis. What's the x component of this velocity? Yes. Plus 1/4 of the x component of my velocity leaving the system through this outlet. And what is that x component? Exactly. So we get 73.5. That's my magnitude of the velocity vector times cosine of how much? 60 degrees. So everybody agree with this number? Okay. Minus the x component of the velocity entering the system. And what's the x component of the velocity entering the system? The what? Cosine, yeah? Cosine of 45. Remember what we have here? We got 45 degrees, right? Horizontal line, 45 degrees. So 45 degrees. So we get 73.5 times cosine of 45 degrees. Look at that. Whatever component I choose for velocity, it will always be a function of 73.5. So if you wanted to, you could even factor out the velocity magnitude, if you want. If you factor out the magnitude of the velocity and you end up only with your angles, then you're going to end up with the deflector equations, right? But for now, let's just focus on what we already have. Okay? So how many unknowns in this equation? No unknown. Well, one unknown, right? The sum of forces. So we can look at the system and we say, okay, we can treat this as a deflector because it's deflecting fluid. And in the x direction, Rami, in which direction do you think the force needs to act? Okay. So we get that there is a reaction force in the x direction. So these sum of forces should just include the reaction force in the x direction. Okay? All right. Let's solve this. Can anybody solve this? Give me a number, and can somebody else confirm that number?
33.3 pounds in the negative x direction.
So negative Rx equals negative 33.3 pounds? Good. Thank you. Of course, this is the reaction that's keeping the deflector in place, right? If I were to ask you what's the force that the fluid is exerting, then it's just the opposite direction. That's all it is. The reaction is going to be in this direction. The force is going to be in this direction. Notice that Rami guessed the direction correctly, because if you multiply both sides by -1, you get that Rx equals a positive number, which means that he guessed this direction correctly. This is the force in which the deflector is resisting the fluid. Okay? Up to this point, I know this is a... Well, I've been talking for half an hour. I thought it's been like 5 minutes. Up to this point, are there any questions? If this were on the test, would you feel comfortable solving it? Yeah? Okay, let's find the y component. And hopefully, if we have time, let's make this problem harder. But let's do the y component first. Okay? So because this is easy, and we can agree, right? This is, as long as you understand how to set up the equation first, I think everything else should be easy. I would like for one of you to try to solve it in the y direction. So let me just write the equation that we came up with. We got that sum of forces would equal mass flux in times 3/4 of the y component of the velocity leaving the system plus 1/4 of the y component of the velocity leaving the system minus the velocity entering the system. We know what mass flux is. I'm just going to write it down, 0.778 slugs per second. In which direction do you think the y resistance is acting? Upwards? Okay. So Rami guesses that it's upwards. We'll see if Rami is correct or incorrect. Because it's upwards, I'm going to leave this as a positive value. All this multiplied by 3/4 of the y component of the velocity leaving the system through outlet number 1. The velocity, right, is 73.5, the magnitude. So what is the y component of this velocity? All of it, right? 73.5. Okay? Let's look at it. So we got 73.5 feet per second. What am I missing?
I think that it's not going to go down.
Sorry?
It's easy to go down, so all of them will go down.
Yeah. So what am I missing here? Sorry?
A negative.
A negative sign, right? Remember, we're taking our x-axis to be horizontal to the right, or y-axis vertical upwards. But notice that this velocity vector is moving downwards. Therefore, the y component of that vector should be a negative scalar value. Okay? So we get negative 73.5. And that's a very important distinction to make, okay? Plus, we get 1/4 of the velocity leaving the system through a second outlet in the y direction. What would this component be? In the y direction, what would this component be? This is 60 degrees. What's the y component of this? Sine 60. Okay, there we go. There we go. I had a bad dream one day that somebody was answering 0 to that question. But it's okay. It was just a dream. Nothing happened. Nobody heard anything. Minus the y component of the velocity entering the system. Mm-hmm. I'm going to write the units. Sine of 45. What am I missing here? Right? If you were to draw this vector into its two components, what am I missing here? A negative sign, right? Because the y component is moving downwards. So minus minus is plus, right? Good. One unknown, ry. We can plug it into our calculators and solve it. Let's go ahead and solve it.
Negative part again?
Yes, here,
Yeah.
because
Isn't it flowing this way out?
flow is moving in this direction.
Oh, that's the, never mind. Yeah.
That's the inlet. Yeah.
Okay. My bad.
This one is positive.
Yeah.
These two are negative.
I was looking at it wrong.
It's okay. So what's that component?
So it's going to be negative for sure.
You think so?
I got 9.9.
Wait. So we got, I hear a 9, I hear 40.
Negative 9.93.
Negative 9.93, is that what you got?
Yeah, that's what RY is.
All right, let me, so there's different numbers. Let me consult with the book.
I got 9.9. Yeah.
All right. 9.93,
I got Y is equal to negative 9.93.
positive?
Yeah, I got
You got positive?
I got positive.
All right.
Wait.
Okay, I will say, let's make sure that we all get the same answer. Not for my sake, but for yours. So notice that we have one negative value, that's correct. But we actually have two positive values, right? This negative value, notice that it's actually 3/4 of the entire velocity component. This is 1/4 plus 1. This is 5/4 of the entire velocity vector. So this answer will be positive. It has to be positive. Because if you factor out the 73.5, you factor out the 73.5 sine 6, well, just 73.5, you have 3/4, or negative 3/4 plus 1/4 sine 60 plus sine 45, 1 sine 45. You should get a positive number, I think. So what, is it positive or negative?
I got positive.
Okay. If you didn't get this number, let's see, maybe I'm missing a parenthesis. Yeah, I'm missing a parenthesis here, right? This one closes with this one. Maybe that's it, okay? Whew. Any questions? Pretty easy enough. Yes?
That question asks for the Rx and RY value. Is that what that?
It asks for the force.
Okay, right.
Yeah, so let's say you have your Rx and Ry value. How do you find the force? Yeah, just square root of the sum of the square of two terms, right? Yeah. But,
Yeah, right.
sorry?
Is that in pounds?
RY.
Yeah.
Yes, of course, in pounds. Good catch. So yeah, if it asks you for the entire magnitude, just rx squared plus ry squared, take the square root of that. Okay? But I think for this exercise, right, this formulation is what I care about, right? As long as you understand this, you should understand momentum in fluids, okay? So can we make this problem more complicated? Yes. Okay, so let's go ahead and make this problem more complicated. I know that you're looking at me like, what is this, kindergarten? Give me something that I can handle. Give me something that makes whatever thousands of dollars I pay for my tuition worth it. So I hear you. I don't hear you, but I still give you something a little more complicated. Okay, this was all fun when our deflectors, right, are static, or at least pseudostatic. This, is pretty manageable, right, as long as we know that the deflector is static. What happens if your deflector is moving? For example, what happens if your car is driving in one direction and the wind current is in the opposite direction, and you want to calculate the force of the wind on the windshield of your car? You can't treat this as a static deflector because the car, your deflector, is moving, and you have additionally some flow rate, right, from the wind currents. So the question is now, how do we rearrange or reorganize this system of equations in order to account for moving control volumes? And the answer is actually easier than you think. But what do you think now? Just like guessing or maybe trying to formulate it. Well, what changes if your deflector is moving? Sorry?
Is it the angle at which they're deflected? Or it depends on the system.
Okay, yeah, you're right. It depends, right? It depends on how the system is set up.
Also the flow rate.
Let's look at an example. What happens if, can you give me an example of a moving deflector? Don't say the car, something else.
Airplane wing.
Sorry?
Airplane wing. Of course, your velocity.
Fine. What happens? Let's say your airplane is sitting there static. It's. Do you say airplanes are parked? What do you say about airplanes? Cars are parked, right? Airplanes are grounded. And you have a wind current. Your wing is not moving, but you have a wind current. You can treat it as a deflector. Good. But then let's say that you have the same wind current, right? But your airplane wing is moving towards the direction of the wind current. Or, like towards the wind. Do you think the force increases or decreases? Increases. Why does it increase?
The velocity of the plane, you have to account for that too.
Exactly, right? So if you are standing on the wing, right? If you're standing on the wing and you're looking at the wing as if it were a static object, what you're experiencing from your point of view is that the wind is actually greater, right? Faster.
Relative speed.
Exactly. There we go. Relative speed. Have I already talked about relative velocities and stuff like that? Maybe not yet. It's okay. Here's the example. Nash is driving his car on the highway. Well, actually, I'm driving my car on my highway at 55 miles an hour, which is the posted speed limit, because I never go over that posted speed limit, even though I'm Hispanic. And then Nash zooms by next to me at 90 miles an hour. I'm 55, he's 90. Okay? The question is, do I see from my car, do I see Nash moving at 90 miles an hour? At what velocity do I see Nash moving at?
35.
Right? What did you say?
35.
Whatever the difference is, right? I think it's 35, right? Yeah. Okay, so whatever that difference is. Good. So that's one thing. That's relative velocity when we're moving in the same direction. Now again, I'm driving at 55 miles an hour, the posted speed limit, because I never go over it. And then Andy drives on the other lane in the opposite direction at 40 miles an hour. At what velocity do I experience Andy driving in? Exactly, right? Whatever that number is. Let's not embarrass ourselves. Let's just say whatever the addition of those two numbers is, okay? So that's how relative velocities work, and that's how I want you to visualize these deflectors. Always think of yourself as the passenger in the deflector. And if you do that, this problem will actually, even though it's harder, it will actually look just as easy. Because if you are the passenger, right, in this deflector, then all you have to do to account for the extra or the less velocity is just look at the relative velocity between the deflector and your fluid flow. Okay? So let's do an example to understand, make sure that we understand this concept. And I think this example will be a good place to end today's material. Okay? So in this example, we're going to be looking, for some reason, at a car who's being shot at with a hose. Not really sure why. I thought it'd be nice to use wind with your car. Wind makes more sense, but for some reason we're using hose and water. Okay, so this is another example. So what do we have? We have this car. It's a pickup truck, actually. Does anybody drive a pickup truck? Of course. It's a pickup truck that one of you two is driving. Okay? Now this pickup truck is being driven at 5 meters per second. How much is that in miles per hour, in a term that we can understand? Calculators. I just want to know, just out of curiosity, how much is 5 meters per second in miles per hour?
How many meters per mile?
Well, there's 3.28 feet in a meter, 5,280 feet in a mile, and 3,600 seconds in an hour. 11.18 miles per hour? That's not too fast. So this pickup truck,
Maybe you're driving it.
I resent that, and I will remember that when I'm grading. So maybe,
I'm driving it.
sure you are. So we're driving this car at 5 meters per second, okay? The windshield has a deflection angle of 45 degrees, okay? All right. For some reason, a 50 millimeter diameter stream of water hits the car. So somebody is pointing a hose with a diameter of 50 millimeters and then shooting fluid at the car. And what happens is the fluid gets deflected through the windshield, just as the fluid should do through the windshield. Okay? The discharge through this hose is 8 liters per second. Somebody start computing that, calculating that in cubic meters per second. I think liter, I can just write it as capital L. I think that's easier. 8 liters per second. What is the force that this stream of water under standard engineering conditions exerts on this truck? Ooh. First off, in what context would somebody hold a hose against a moving car and shoot water at it? It's an honest question. Car wash? Okay, there we go. They should just say car wash. So you're washing your car, and for some reason the car that you're washing is moving towards you. Okay? 11 miles an hour is actually pretty fast for a car wash. So you're washing your car. You're pointing this hose at the car, which is moving towards you at 11 miles an hour. Okay? The question is, what is the force that this windshield is experiencing? So first off, we look at this. Where's my control volume? Where should I place my control volume in order for me to be able to solve this system using momentum equation? Start from the hose? I mean, it doesn't have to go that far, but start before the bend at least, right? Okay. All right, so before the 45-degree bend, right? And where should it end? After, right? Sometime after. It doesn't really matter. I mean, you can start from the hose and here, but really the important thing, right? What I want you to know is that your control volume has to start before the bend and has to end after. Good to see you, Zach. So we look at this control volume. But now I want you to put yourself in the place of the driver. So relative to this control volume, right? I look at my control volume. Is the flow rate that this control volume is receiving equal to 8 liters per second? No, right? Why not?
It's because it's moving while you're moving towards you while it's start.
Exactly, right? As the flow moves towards the control volume moves towards the flow. So should you experience a greater flow rate or a lesser flow rate? Greater. Good. So we're on the same page here. Good. So we got our flow rate. Our flow rate of 8 liters per second. Can somebody convert that to cubic meters per second?
8,000.
8,000?
Okay. It's the other way around. 0.00.
Who said 8,000?
I did.
He's gonna remember it when he grades your paper.
He doesn't remember my name.
And you made it work.
I don't remember your name, but I remember the top half of your face. So when I'm looking at you in the oral exam, I'll probably ask you to cover your mouth, and I'll be like, yeah. That's the one that said that I drive slow. Okay. All right. 0.008 cubic meters per second, that's good. Let's go ahead and calculate that velocity entering the control volume. Maybe not entering the control volume. Let's just calculate the velocity of the fluid leaving the host for now. Okay. So leaving the host, the velocity is equal to what? How do I calculate it? Q over A. Okay, good. So we got flow over area. I got 0.008 cubic meters per second. I have an area of pi over 4 times the diameter. That's 50 millimeters. Is 50 millimeters 0.05 meters? Okay, so 50 millimeters, so 0.05 squared, and this will be a meter squared. And this gives me a velocity of how much? 4.07? Can somebody confirm? Yeah. Okay, so this is the velocity of the fluid as it leaves the hose. But now let's look at it in terms of the control volume, right? In terms of this control volume, what is the velocity that's entering the control volume? What do you think?
5 meters per second.
Sorry?
5 meters per second.
Is that the velocity?
No.
There we go, right? So you have flow coming in at 4.07 meters per second. You're moving at 5 meters per second. And what's the velocity at which the flow enters your control volume?
You got them all.
Exactly, right? So we get 4.07 meters per second plus 5 meters per second, which gives us 9.07 meters per second. That's the velocity of the fluid as it enters the control volume. Is that correct? Are we on the same page here? Good. Of course, velocity travels through this control. Yes?
But they're going in different directions, so why are you adding?
Well, you got 4.07 in my direction. I'm moving forward in this direction. So you're experiencing more, right? Let me think of an analogy.
If you're running away from a bullet fast enough, technically the bullet will never hit you.
Yes, very realistic analogy that we can all relate to. So if somebody shoots at you, just run. And if you run fast enough, then you'll understand why we're adding and not subtracting. Can somebody give me a better analogy?
No, that's the best one. Running towards the ball.
Well, I guess we're stuck with that analogy. But does it make sense why we're adding?
The formula for the relative velocity has a negative in it to begin with, is how I look at it.
Okay.
VB minus VA, and then if one of the velocities is negative, it cancels that.
Yeah. See, I like to explain things physically, not mathematically. I love math, but I like to have physical explanations, so I got to think of something else. I know. Let's go back to the cars. So you're driving, right? At what speed do you drive in the highway? No judgment. So you're driving at 75, right? And let's say that you hit someone that was driving at 55. So I'm driving 55, you hit me, okay? So we're both driving in one direction, you hit me. Let's say that you hit me, but this time we're driving in opposite directions and I'm driving at 55. Which one do you think will hurt more? Opposite directions. Why? Because the force gets added, the velocities get added up, okay? So if you see me on the highway, I mean, don't hit me, right? But if you see me on the highway, you know that if we're driving in the same direction, then our velocities will be just subtracted from each other. But if we're driving in opposite directions, we add up our velocities, we get a higher velocity, higher impact. Does that make sense? Good. Let's go back to this problem. Okay, we know from our deflector equations that the velocity magnitude doesn't change for the deflector, which means that this velocity leaving my control volume is also 9.07 meters per second. Now remember, this doesn't mean that the fluid particle is moving at that velocity. It just means that the control volume is experiencing it at that velocity. Does that make sense?
Okay.
The actual fluid particle is moving at a different velocity. Okay? Does that make sense?
Yeah, because I had a question about that. Because I was going to say, like, the airplane wing, like, it actually travels faster over the top than it does the bottom.
Yeah.
You know, so okay.
Yes. So, yeah, this doesn't mean, again, this doesn't mean that the fluid particle is moving at a faster velocity. It just means that your control volume experiences it moving at a faster velocity. Okay? Good. So, we have our control volume. And now, do you think we can start just applying the equations like we did in the previous exercise? Or do you think there's anything else we need to adjust? What do you think, personally? Sorry? I can't hear anything you're saying. Well, we have to, yeah, for the x and y directions. That's correct. We're going to have an x component, we're going to have a y component. So it looks like as long as our velocities are accounted for, yes? Atmospheric, yeah, that's correct. Atmospheric. For the deflector, it's going to be atmospheric pressure. So we don't have to worry about it. So do you think we can start solving, or is there any other adjustments we need to make? Okay, let's go ahead and start solving and see what that looks like. So we write down our momentum equation. The momentum equation doesn't change. We get sum of forces in the x direction equals mass flux in, out. Mass flux out, velocity out, minus mass flux in, velocity in. There's only one inlet, there's only one outlet, we only have one component. Technically, we could factor out mass flux, but before we do factor out mass flux, I need you to understand what this mass flux represents. We know that mass flux is equal to density times flow rate. So is the mass flux in this control volume equal to density times 0.008? Why not?
It's the relative velocity.
Exactly, right? So let's not make the mistake of thinking, well, we have mass flux. In order to make things a little bit more manageable, the way I like to write it is to express everything in terms of, or in relative terms. So I'm going to say relative mass flux, okay? Relative velocity. And this is in the x component. Relative mass flux. Relative velocity. That's just out of simplicity. So, now that we know that we're dealing with the relative components, we can go ahead and calculate our mass flux. We know that mass flux is density times flow rate, and we know that flow rate is velocity times area. If we want the relative mass flux, that means that we have to use the relative flow rate, and that means that we have to use the relative velocity. So we go ahead and calculate our mass flux. We get density of water. What's the density of water for SI units? 1,000, right? We have our relative velocity. What's the relative velocity? 9. Okay, good. 9 point. Is that a 0.7? And then we have the area, which we already calculated as pi over 4.05 squared meters squared. Good. So our relative mass flux becomes what? Or is what? Units?
Kilograms per
Mm-hmm. Yep. Cubic meters cancels out and leaves us with kilograms per second. Good. So we have our mass flux. Now let's look at our velocity terms. And before we even do that, is the mass flux leaving the system relative equal to the mass flux entering the system relative? Relative, both relative. Yeah, it is. Okay. So I'm going to simplify my equation. It's not that my handwriting was better or good at any point, but it was definitely not as bad as it is now. So as the semester progresses, you'll see that my handwriting will slowly start to get lazier and lazier. Probably the last couple of weeks, I'll just be sitting on the chair reading stuff to you. But it's okay, that's how we grow up, okay? So we get sum of force in the x direction equals my relative mass flux times the x component of my relative velocity leaving the system minus the x component of my relative velocity entering the system. What forces do you see here? Well, just like before, we had a reaction force in the x direction, a reaction force in the y direction. So I get that negative Rx equals my mass flux of 17.8 kilograms per second. That's a relative mass flux. What's the x component of the relative velocity as it leaves the control volume? That's correct. So we get 9.07, right? Meters per second times cosine of 45. Minus, what's the x component of the relative velocity as it enters the control volume? At this point, because this is a very standard deflector, you can just apply the equations of deflection that we derived earlier, right? Because if I write the equation of deflector, remember, the equation that we got earlier was Rx equals mass flux times velocity times 1 minus cosine of alpha. And notice that if you just understand that the mass flux and the velocity are relative terms, the equation is exactly the same. Mass flux, right? Factor of velocity, you get cosine of alpha minus 1, but there's a negative sign, so you flip these terms to turn it into a positive. So it's the same equation, except that we're dealing with relative terms. You choose whatever method is best for you. Okay? So based on this, what is my force component in the x direction?
Negative 47.3.
3?
Yeah.
Units? Oh, so you said negative Rx equals negative 47? Oh, okay, there we go. So Rx is just 47.3. Is that correct? Okay, good. Of course, we go to the y direction. And we say that in the y direction, my sum of forces equals my relative mass flux times my relative velocity out y minus my relative velocity in y. We already know in the y direction we have one positive Ry force. My mass flux is 17.8 kilograms per second. What's my out velocity in the y direction? Yep, 9.07 meters per second times sine of 45. What's my inlet velocity? 0. Good. And you get again the same equation that we derived earlier. Ry equals m dot times v times sine alpha. It's the same equation. So what is my force in the y direction?
114.2.
Can somebody confirm that? Units? I'm getting slightly different values, just like a couple of numbers slightly. So we'll look into that in a second, okay? So up to this point, are there any questions with solving this problem? Yes?
I know we have to take the relative flux, but I don't know why again. Can you just explain why?
Of course. So you have your control volume, which is moving, right? Of course, you understand why the velocity is different, right?
Yeah.
But remember that for every particle that moves linearly, there's an area of particles that are moving with it, right? And combined with the length, that's volume, right? So what you have is essentially a volume of fluid, entire volume, entering your control volume at a speed of 9.07 meters per second, right? So it has to be your relative flux, because even though the mass flux of whatever we get, 0.0008 times 1,000, I guess 8, the mass flux of 8 kilograms per second, even though that's what leaves the host, what enters your control volume is more than that, right? Because you're moving towards it. Okay, and that's why we have to use the relative one. Okay, any other questions? Yes?
So once we find that our forces equal to the mass flux relative times our difference in our velocities, can we just use those equations that were given in the deflection equation?
Yep.
Okay.
Just make sure that you use the relative terms.
Okay.
Yeah, as long as you use the relative terms, you should be fine. Okay. So the equations are organized the same way. Let's see, we have velocity. Oh, I see why the numbers are different, because the book uses 40, I use 45. That's all it is. Everything else is the same. Okay. Thought that I taught you incorrectly. I was like, oh no.
But
Should
there's
I?
one last step.
What?
You still have to find the resultant force.
And how do we do that?
I don't know, I mean, just square
Yeah,
root.
just square root. Okay. Yeah, I think normally I in my tests, if I remember correctly, I asked for just the components, right? Or did I ask for a resultant force? You don't remember? Okay. So I think I only asked for components. See, if it turns out that the angle was correct and it was the procedure that was incorrect, I would have had a dilemma, right? Should I tell you that I was wrong, or should I just let you think that you know your stuff? Being who I am, who knows? Maybe you will design a very bad windshield one day because of me. No, but it was right. We did it right. I just used the wrong angle. The book uses 40. That's it. So that's the procedure. Before we finish this topic, are there any questions? We need to answer any questions because next week we're doing something completely different. So any questions? Next week, differential analysis of fluid flow, or just differential fluid flow for short. If you're not taking DiffyQ, it's okay, but you will learn it next week in detail. So study your calculus, study your integrals, study your derivatives, study your chain rule, study your product rule, study your Taylor series expansion, study all that stuff, because we're going to bring it all and apply it to fluids. Next week will be, without a doubt, the hardest material that we're going to cover the entire semester. So bring your A games and, come to class and whatever. Do your homework.